LLM savings are easy to claim and hard to prove. In this lesson, we'll trace cost down to individual tokens, connect architecture choices to reliability, and turn observability data into financial reporting that both engineers and executives can trust. We began with a fragile LLM application, expensive, slow, failure-prone, and difficult to trust. Then we redesigned the platform, added reliability patterns, and built observability around latency, quality, versions, and drift. Now those pieces come together. Token-level cost attribution is where architecture and monitoring become financial evidence, showing exactly what drives spend and where value is created. A monthly LLM invoice tells you what you spent, but not why. Token-level attribution reveals the actual drivers: requests, users, tenants, prompts, and model routes. That turns vague spend into unit economics, so optimization becomes targeted, measurable, and safe. Cost attribution depends on a consistent metadata contract for every request. Start with business context. Who made the request, which tenant, segment, feature, workflow, and environment it belongs to. Then capture the LLM context: model, provider, route, prompt version, routing policy, and any fallback reason. Add usage data: input tokens, output tokens, cache status, batch, and latency. Finally, log the outcome: success, timeout, error type, quality score, retries, and fallback success. With these dimensions in place, cost stops being a monthly surprise and becomes traceable to products, customers, and decisions. The attribution flow starts at ingress before routing changes the request. Capture the caller, product, tenant, and business context needed later. As the request moves through routing, cache, model providers, and fallbacks, enrich each span with the chosen model, cache result, token counts, latency, and outcome. Pricing logic then joins those facts with API rates, GPU amortization, storage, networking, and orchestration costs. The output is an immutable cost event, traceable enough for audits, detailed enough for analytics, and trusted enough for billing and executive reporting. Before claiming savings, establish a baseline you can defend. Measure the old API-only setup under comparable traffic instead of relying on the monthly invoice. Include token spend, retries, failed calls, premium model use, and overgeneration from prompts that produce more than the product needs. Break cost down by feature: tenant, model, prompt version, and request type. Then pair cost with reliability: success rates, timeouts, degraded answers, and user-visible failures. Savings only matter when the comparison is clean. A lower bill after optimization does not automatically prove the system became cheaper. Traffic may have grown, seasonality may have changed, prompts may be longer, or premium features may be used more often. The fair question is cost per comparable unit: per 1,000 requests, per successful completion, per active account, or per workflow. Hold request volume, token volume, feature mix, tenant mix, and time window constant. If the baseline and optimized systems cannot run in parallel, build a counterfactual. What would the old system have cost under today's workload? Only then can savings be trusted. To make a cost reduction claim credible, compare like with like. Normalize both periods to the same unit, such as cost per 1,000 successful completions. Then calculate savings as 1 minus optimized cost divided by baseline cost. In this example, $10 falls to $3.80. That means the optimized system costs 38% of the original, or 62% less. Completeness matters here. Include API calls, GPU serving, cache, storage, orchestration, and monitoring. If GPU amortization or modeled baselines are involved, report a confidence range. A strong savings story does more than say, "We cut cost." It identifies the engineering levers behind the number. Semantic caching removes duplicate work by answering repeated requests from stored results. Smaller, fine-tuned models handle routine traffic without premium API prices. LLM and batching improve GPU utilization, making each generated token cheaper. Quantization reduces memory needs. Prompt compression cuts token volume. Routing limits expensive fallbacks to cases that truly need them. When each contribution is measured separately, the cost reduction becomes explainable, repeatable, and trustworthy. Token economics starts by turning every inference into a comparable unit, dollars per useful result. With a hosted API, the basic calculation is simple. Input tokens times the input rate plus output tokens times the output rate. For self-hosting, the math is broader. Divide GPU and operations cost by the number of tokens actually generated, adjusted for utilization, batching, and idle capacity. Watch the common trap. Output tokens often drive both cost and latency, so shortening prompts alone may not move the needle. Track cost per successful completion, not just cost per request. Financial savings only matter if users still get a better result. Reliability needs the same before and after proof as cost. Track availability, successful completions, timeouts, errors, and degraded responses, then compare each one against the SLO. Also measure fallback success because a rescued failure may be invisible to the user but very visible in the architecture. Claims like doubled reliability should be defined precisely. For example, failed completions cut in half or successful completions within deadline doubled. That makes the claim measurable, defensible, and repeatable. Cost optimization becomes risky when we measure only the price of a single request. A cheaper model or route may look efficient, but if it fails more often, responds slowly, or produces unusable output, the system pays again through retries, fallbacks, longer latency, and support work. That is false savings. Evaluate every option against cost, quality, latency, and completion success together. Reliability controls are not just safeguards. Caching can avoid repeated calls, and circuit breakers can stop expensive failure loops. The practical target is cost per successful, quality acceptable completion within your SLO. That metric rewards savings users can actually feel. Reporting should not create 4 different versions of reality. Start with one request level ledger, then shape it for each audience. Engineers need the operational view: routes, models, tokens, cache behavior, latency, retries, and errors. Product teams need the same data rolled up by feature, workflow, tenant, and segment. Finance needs spend, margin, forecasts, and unit economics. Executives need the shortest version: what improved, what was saved, what risk remains, and what to fund next. The abstraction changes, but the source of truth does not. Executive reporting should make decisions easier without turning the analysis into a black box. Led with outcomes: normalized cost reduction, absolute savings, reliability, and margin impact. Then preserve trust by showing how the numbers were produced: the baseline, the post-deployment window, what was normalized, which costs were included, and the confidence level. Just as important, show the trade-offs. Savings are less meaningful if latency, quality, fallback rate, or operational complexity moved in the wrong direction. The best pattern is an executive summary backed by engineering appendices, so leaders see impact and technical reviewers can verify it. Token-level cost attribution makes impact provable, not anecdotal. Instrument every request and tag tokens by model, route, tenant, feature, prompt, cache state, and outcome. Attribute savings to specific engineering changes, then validate the 62% reduction against a normalized baseline. Finally, report cost alongside reliability, success rate, timeouts, fallbacks, and SLOs. Next, we synthesize everything in the capstone architecture.